Ray, I think you're muted. Yeah.
I'm sorry about that.
Yeah, we hear you. Are you are you able to put it a little bit bigger, your slides, or is it?
Yeah, yes, I should be able to. This better?
Yeah, perfect.
Okay. And is it moving back and forth?
Can you go down? Yeah, it's moving back and forth. All good. Thank you.
Good. Okay. Shall I begin?
So, well, we have the great pleasure having Dr. Ray Hawkins, who is our managing editor of our new journal, Quantum Economics and Finance, Sage published. Ray was at UC Berkeley in economics and is also attached to the University of Arizona, has also worked in industry, and is this, as I mentioned, our managing editor for Quantum Economics and Finance. So Ray, the floor is yours. Please.
Thank you, Emmanuel, and thank you, Nathan, as well for organizing this workshop. Very interesting talks from my perspective so far, so I quite enjoyed it. Going to be summarizing some work that I have done with my colleague, Roy Frieden at the Wyatt College of Optical Sciences. He is the individual who developed the Fisher information approach that I will be discussing and using in a financial economics context. So let's sort of jump into it. The overview, I'm going to sort of just leap right into how Fisher information is related to a quantum formalism. Hopefully, from those of you who are familiar with information theory, in particular maximum entropy and getting distributions that way, or if you've worked in statistical mechanics and used constrained optimization of information to get various distributions like the canonical and microcanonical distribution, some of this is going to have it's going to ring a familiar chord, hopefully. What hopefully will be interesting, though, is what you can do and what you can get by using Fisher information instead of, let's say, for example, Shannon information. I'm going to approach it from two perspectives. First, the time-independent approach. I'll show how you can generate a time-independent Schrodinger wave equation using this approach, and then apply it to forward and option contracts in finance. And then I'm going to be looking at showing you how you can use the same approach to look at a time-dependent, and actually derive a time-dependent Schrodinger wave equation, which leads to the whole world of Bohmian financial economics. The approach that I'm going to be following is one that I sort of adapted to a financial economics context from the work of Reginato on this, who put this out as a general Fisher approach to quantum mechanics. And on the Bohmian side of things, Professor Haven is sort of the leading light in terms of Bohmian applications and actually doing empirical work along those lines, which is really quite interesting. So hopefully this talk will tie in with a number of the ideas that we've seen discussed in this workshop, and also in work that's appeared in the literature. And then finally, since I'm sort of going to come at it initially from why do quantum? It's cool, why not? Get a little bit deeper into, well, okay, is there something more to it? Why use quantum in finance and economics? Which, given my position with the journal, I better have a pretty good answer for. So hopefully I'll convince you of that. So what's the basic idea? This, what I'm about to describe, is a very standard approach to developing the formalism for Fisher information in a constrained optimization format. So we take, in our case, the observed price of a security, and we think that, yeah, you observe, but what you observe is not necessarily the true value. There's just an associated fluctuation, and that's given by this equation here. And then in our particular analysis, we're going to assume that the statistics are independent of the price level. There are other ways that you can approach this in terms of assumptions. If you have priors, let's say that there are material fat tails in your distribution. but this was sort of the more, this what I'm going to show you is the common framework that you would start at. And then, for those who have other constraints that they want to put on, hopefully, once I've gotten through the talk, you'll have a sense of how you would go about modifying it accordingly. Okay, so probability of the observation given the true value is taken as probability of the difference, and we'll just write that as P of X based on this equation up here. And then we're going to make this statement that is typically associated with quantum mechanics of, oh, well, a probability, we can represent that in terms of the product of amplitudes, in this case, the star indicating complex conjugation. Now, at this point, a lot of people will sort of raise their hand and say, wait a minute, you're doing a quantum thing. Well, the use of amplitudes predates quantum. In fact, Fisher used amplitudes, and his argument for using amplitudes was it makes the math easier, so why not? So I think in the spirit of Bob Koch's talk yesterday, there needs to be sort of a broader sense of when we're using something, is it strictly quantum? Is it not strictly quantum? What does it really mean? And do we really care in terms of analyzing it? Now, later on, towards the end, I'll make the case for why quantum actually matters as a fundamental approach to this. But for the time being, we can say, okay, it's a mathematical way of approaching it. Let's see what happens. One. Okay. The way that you would look at this from a Fisher information perspective is to simply write down the classical Fisher information for this type of process or this type of problem. And what you would come up with in that analysis is this expression up here. And the angle bracket is an expectation over all possible data. Wonderful. But from a practical perspective, what does this give us? Well, when you look at the kind of problem that we're looking at, this reduces to this very common expression down here, I equals the integral of 1 over p, partial p dx squared. And if you write that in terms of the amplitudes, you actually get it in terms of the slope of the amplitudes here, the modulus of the slope of the amplitudes. So this is the information expression from a Fisher perspective. And it's a little bit different than ones you might have encountered. If you're familiar with the Shannon information, we don't have P log P in here. Fisher is focusing more on the slope or the magnitude of the slope of this. So if you're minimizing the information, you're minimizing the slope of the corresponding amplitudes, which has a certain intuitive niceness to it. Okay, so we have an information measure or expression. What do we do with it? Well, again, going back to the max-ent approach, which some of you are probably familiar with, or the use in statistical mechanics, you have something about the system that you know, or that you think you know, that you understand. Measurable data, for example. Measurable data will tend to constrain the type of probability densities that are associated with the observation. And we go along the same path here as you would with, let's say, a max-ent approach, and simply form a Lagrangian. And you can see what I've done down here. I have a Lagrangian, so I have the Fisher information in this term here. Then I have the constraint that the probability integrate to 1. Okay, nice thing to have. And then I have further constraints based on the idea, assuming that my observables can be represented as expectation values or averages of known functions, which in my case is going to be the case. I can write these terms here, these constraints, is basically saying, whatever probability distribution you come up with, it's got to reproduce what we observe. And the lambdas here are simply the Lagrange multipliers associated with the constraints that we are bringing to bear. Okay, so far so good. Where's the quantum, Ray? Well, very interestingly, when you apply standard variational approach to this, you end up with this expression here for the amplitude. And if you look at the structure of this equation, here we have the Lagrange multiplier that was constraining the probability to be integrated to 1. We have the Lagrange multipliers and the functions here that are the known values that we have measured averages of. This equation is very much similar to the well-known Schrodinger equation. So at this stage, we can say we have a Schrodinger-like equation, but Schrodinger-like equations are sort of fun to work with, right? You know, we now have access to an entire body of work of solving Schrodinger equations to get amplitudes, and then be able to look at those amplitudes and see how much we might use them to better understand financial economics. Okay, so the main thing that we would be needing to worry about here is what are these, where does the potential come from? Because if you've ever done this before, in a quantum course or elsewhere, it's like, okay, given the square potential, that is the solution to the Schrodinger equation. Given the linear potential, what's the solution? Okay, where does the potential come from? The potential comes from this linear combination of these known functions. And in the case of derivative securities in particular, you know what those known functions are. So let's take a look at an example of this. I'm going to consider the pricing of a security known as a forward or a futures contract. They're basically the same. There's a slight difference in terms of where they're traded and how margin is calculated for them. But the bottom line for both of these contracts is that they are an obligation to buy or sell, depending on the nature of your position, something in the future. And these have, interestingly, the simplest of all possible functional diagrams here. It's basically the value here, x, and then discounted back to today. And why is it that that's what e to the minus rt does here? The r is the interest rate, t is the amount of time between now and when you would be doing the buying or selling. And so this e to the minus rt basically tells you how much is a dollar that is going to be needed to either be bought or sold in the future worth today. But the sort of more important feature that for us is this x term. So this basically gives us an equivalent potential. This function is just a straight line. And since we are working on the half space here, or I'm assuming that the underlying, or x here, underlying is sort of a financial economics way of talking about x, is strictly positive. So think of a common stock that's traded. You can obviously go beyond this, but this is sort of the simplest way to get started in this. And in that case, well, what do we have? Well, the probability can't go less than 0. It's got to be greater than 0. It's a linear, what we would call payoff diagram, or a linear potential in this case. And so in this graph, what I'm showing you is potential and amplitudes here on the y-axis, sorry, and then the level of underlying the x on the x-axis. So the associated potential is this solid line here. And then you can look it up. What do you have? These are Airy functions. These are known. And so I'm showing you the first 4 solutions for the amplitudes for the Schrodinger equation. I've just offset them by unit amounts so that you can see them, you can visualize them relatively easily. So linear potential, Airy functions, very straightforward. One of the nice features about this, let's say contrast to something like maxent, is that maxent will give you typically like the ground state and not a whole lot else, without a whole lot of modification. I'm sure there are people out there who can get very clever with maxent, but for the standard maxent normally that I've ever run into, you get one solution. This gives you a variety of solutions. It also starts to give you a sense of, well, if market volatility, which is often proxied by the width of the associated probability distribution, was to get larger. So that width was to grow. Why would that be happening? Well, when you see that this potential function has as possible states to populate a variety of amplitudes that have a larger extent, you can immediately see that, yes, a shock to the economy would give rise to populating the higher order states, and that would naturally just broaden out that distribution. We would recognize that as volatility went up. And then as those states are depopulated over time, volatility comes back down. So right there, we're sort of getting a basis for representing volatility fluctuations that other methodologies would have been, let's say, a little bit more challenged in showing. So this is one of the simpler structures that's out there, and it's sort of a canonical go-to, can you price a forward or a futures contract? How would you go about doing it? What I'd like to show you now is something that's a little bit more complicated, the idea of using option prices. And there are two types of option prices that we'll consider that I'll just briefly discuss here, the call and the put option. The F value, the thing that goes into the integral that gets multiplied by P and then integrated all over. In the case of the call option is this discounted value or discount function like we had before, times the max of the level of the underlying minus this K value and 0. So what this is saying is I have in the case of a call, I have the right but not the obligation to buy in the future. And what this is basically saying is that if the price is greater than K, I will buy. If it's less, I won't, and I'm not going to have any penalty. Whereas in the case of a forward agreement, whatever happens in the future, if I've agreed to buy, I have to buy. If the price goes up, woohoo, I've made money. But if the price goes down, I've lost money. In the case of an option, the price goes below K, I don't need to do anything. Payoff is 0. The put is the right but not the obligation to sell in the future. And so it has just a reverse here. In the ordering of K and X. And basically that means that if you agree that you're going to sell, let's say at 50, and the price on the day that you have to do the transaction is at 30, life's great for you. You go in, you buy it in the market at 30, sell it at 50 to the person who's obligated to buy it from you at 50, and you make money. On the other hand, if the price has gone up to, let's say, 70, and you've agreed to sell it at 50, you don't want to buy it in the market at 70 and then sell it at 50 and lose 20. So you just decline to exercise the option and the payoff would be 0. And as before, R is the interest rate, T is the time frame over which this contract exists. So let's say I had the case of a portfolio that I'm looking at, and I've got a futures position in it, or forward position, and an option. How might those securities come together to create a potential that I could then calculate a probability density for? Well, we saw before that in the upper left hand, I'm showing you what a typical futures contract would look like. And that's just a linear function here, as we saw 2 slides ago. In the case of a call option with a strike of, in this case, 1.5, the payoff is 0, the value is 0 below, and then 1 for 1 above it has this payoff. So these are the two functions that I'd be working with, the f sub m's that I'd be then multiplying by Lagrange multipliers to create a potential. Now, a way that could be done is if I took this function in the upper left-hand panel and multiplied it by, let's say, -2, then I would have something that compositely went down like this. Now, if I also have the upper security here, the call option, let's say I have 4 of those, then this will now come back up like this. Well, if this is the net potential, I basically have this nice V structure. And again, you can run to your quantum book and you can look up solutions to that. And here are the first two states that are associated with this potential. So one of the nice things about this is that you can take the security prices that you see in the market and use those as constraints in your formulation in a quantum setting or a quantum context to then work out not only the ground state, but the possible higher order excited states that are associated with that, and be able to use them when you're deliberating about things like risk and what could possibly happen with volatility and historically what had happened with volatility. Now, this can be used in a variety of other contexts. One of the more interesting contexts that we looked at was one involving fixed income securities, where the x-axis is replaced by the time to maturity. We built on the work of Brody and Houston on using probability representations of fixed income securities to adapt this as well. So it's got broader context just beyond futures and forwards. And that's discussed a bit more in the references. So what I'd like to do now is talk about the time-dependent approach. So we have a way using Fisher information of getting to the time-independent Schrodinger equation. What about the time-dependent Schrodinger equation? The other thing that's sort of nice about the time-independent Schrodinger equation is that all of the coefficients were basically Lagrange multipliers. So we didn't have the vexing problem of trying to interpret quantum equations with coefficients that are derived from the physical sciences in a social science setting. In this case, it's going to be a little bit different. We're going to have to do that, but I want to show you the approach that we used as we were adapting Reginato's work here. So the first idea is to consider the notion of velocity. And our approach to thinking about velocity was motivated by this representation here that Reginato points out, that velocity can be related to a real function, s of x of t. Why we need to worry about that, we'll see in a bit. And it has this form. Now, once we hit this equation, the question is, well, what's mass? Okay, and we see a lot of sort of trying to grapple with mass. Is there the equivalent of the Higgs boson in financial economics? I don't know. There might be. But if we step back to work of classical mechanicians, applied mathematicians like Singe, who looked at these problems not from a quantum perspective, but from a classical perspective, they had a view of mass that was a little bit more broadly applicable. Mass, a measure of the reluctance of a body to change its velocity. Well, if you have a price that is moving or in sort of a price space, or a security that's moving in price space, and it's not changing its price very much, you could say in some sense it's got a certain amount of mass associated with it. Whereas a price that's sort of fluctuating around very easily and let's say moves around on days when there's not a lot of trading going on, you can say, well, maybe that has a little bit less what I'm going to call effective mass. And the reason I'm using the term effective mass is because it's used a lot in quantum when you're asking questions about mass, as opposed to, let's say, just mass in a more specific sense. So we're going to start with this notion of velocity, basically the change of s with respect to s more divided by the effective mass. Now, turns out the probability distribution will satisfy this conservation law. And that you can derive this conservation law, and again, this is Reginato's observation work, by minimizing the expression down below, that interval down below. So with that, what can we do? Well, we can set up another Lagrangian. And the Lagrangian we can set up has the Fisher information here. And then we have here the conservation law coming in. And then we have the constraints of any observed prices that we would have in the market, essentially the potential coming in as well. Okay, well, that seems pretty, nice. What do we end up with? Well, we end up with this system here if you vary the information with respect to S and P. And again, okay, that's nice. We have these two equations. What are these two equations? Well, if you interpret this as a Hamilton-Jacobi equation, this S equation here, then you have a potential here and you have another potential here. And for those who are familiar with Bohmian mechanics, you would say, aha, I spy a quantum potential here. The Bohmian quantum potential. Again, something that Professor Hawkins has done a considerable amount of very nice work on. Okay, well, if this is the quantum potential in the Hamilton-Jacobi, how does this relate to a more traditional quantum formalism? And the answer is that if you go and you look at the traditional Bohmian approach to quantum mechanics, he would start with the Schrodinger wave equation. He would then write the expression for the amplitude as this expression up here. And with that, he would end up with equations that look like this. So what we're doing in the Fisher information approach is we're basically running the Madelung transform backwards to get to the Schrodinger equation. And so here we have the Schrodinger equation. We have, again, this Lagrange multiplier lambda 0. We have an effective mass that we've already come up with a way of sort of interpreting from a financial economics perspective. And if we have a particular potential, we could work out what these are. You could do it numerically using split operator techniques, something that has come up, been used quite a bit in quantum mechanics and in quantum-like analysis. What about lambda 0? So, lambda 0 in quantum mechanics is related to h bar. And one of the sort of nice features about this approach is that when you're deriving it this way, you get to this point and then you say, okay, h bar needs to be assigned to lambda 0 to make it traditional quantum mechanics. We're going to go a slightly different direction. We're going to say, well, h bar is not, let's say, social science, in the same way that if you look at the paraxial wave equation, h bar doesn't appear in the associated quantum, or in the associated Schrodinger equation. It's lambda bar. It's the wavelength divided by 2 pi. And similarly for the nonlinear Schrodinger equation for solitons and optical fibers. I'm betraying a little bit of my youth here. It's lambda bar. It's not h bar. So what would our equivalent of this be? And a way to resolve that is to look at Nelson's approach to quantum from a stochastic mechanics perspective. And with that, you can show that the Lagrange multiplier here, and I'm trying to highlight it down here, would be proportional to the diffusion coefficient. So you provide a way of relating that term to something that is, let's say, more naturally associated with traditional financial economics. Okay, so this is, in 20 minutes or so, half hour, the approach to using Fisher information. It provides a very natural way of deriving quantum representations of securities, security prices, and evolutions of probabilities that you can then use in a broader context. So why quantum? First of all, economies and markets are intrinsically uncertain. And whenever you have intrinsic uncertainty, that is sort of an indication, maybe from a traditional quantum perspective, that a quantum approach would be useful. For those of you interested, I would definitely recommend reading Keynes' 1937 short paper, where he responds to a bunch of people who criticized his book, The General Theory. He goes into very direct detail on the instability of markets in general and what we don't know about what's going to happen in the future in particular. There's also an evolving thought on the concept of preferences. In traditional econ, preferences are revealed by elicitation or by experiment. You as an individual have a set of preferences, and the job of the market or an experiment is to get them out. In behavioral, it's like, well, you have, so let's say a superposition of ideas, and then a trade or an elicitation experiment reveals that it's constructed in that moment. It's not something, you're not just sharing what you know about your preferences or your preference order. It is given by that. And this is something from Tversky and Simonson's work that is much more supportive of the quantum approach. And then there's the whole field of quantum cognition. There's a nice review article here by Poltos and Bussmeyer that I highly recommend that basically argues that basically all the agents in markets are dealing with decisions that are made in a largely quantum sense, and that is probably a better way of representing things. For those of you who find this interesting and haven't been exposed to it, or let's say come at it from a, hey, I've done statistical mechanics, this might be fun to do. Here's a set of references that would hopefully get you up the learning curve. And with that, I'm happy to take questions.
Thank you very much, Ray. Thank you.